Good morning, everyone. So today we will have our lecture for week 10 or lecture 10 for unreinforced masonry walls under or subjected to bending and shear. So let's start the content of our lecture. So for the design for member or for masonry walls and bending, we have some notes here. The masonry walls are commonly subjected to out-of-plane lateral loads. Most commonly, this loads either from wind or earthquakes loads. So if this our wall, for example, so this wall will be under out-of-plane earthquakes or wind loads. The design is normally based on the load combination from the standard 0.9 G plus W U for wind. So from AS 1170.0, the main combination or main load combination for lateral loose or lateral wind loose will be 0.9 G and plus WU or plus W ultimate, which is the wind load. The response of the wall or the masonry wall in bending is dependent on the boundary condition of the member. So we have some or three different bending behavior: vertical bending, horizontal bending, or two-way bending. So this means that the behavior of the wall is relevant to the support if it is supported from its vertical edges or from horizontal edges, top and bottom. So we might have like supports from all edges, like 4 edges or some of the edges. So that we have 3 types of bending behavior. The first one is vertical bending. Second one is horizontal bending. The third one is two-way bending. So this is the 3 type based on the boundary conditions. So let's go through one by one. So the first one we have today is the vertical bending. As you can see here in this image, the wall bent in this direction. So if we have support here, so the wall bent in the vertical direction. That's why it's called vertical bending. So as you can assume, where is the supports we have? The supports we have on the top line, this line of the support. So from the roof, so we have this line of support, and also we will have from the bottom line, so it is supported to also the bottom roof or the base. So we have also another line of supports here. Okay, so the failure, as you can see, the failure happened in the middle, almost in the middle of the wall. So there is crack here, and the wall fail at the middle, for example. So here there is no vertical edge support. That's why the wall bent again here, if this is the line. So the wall bent in this direction. And because the wall is not good or the masonry is not very strong in bending, so the failure happened at this point here. Okay. If you have any question, Himanshu, just let me know, please.
Yes, sir, no problem. Yeah.
Okay, so this is our first type of bending, the vertical bending. So let's have a look on the capacity of the wall or the masonry walls in bending or in vertical bending from the standard. The standard is AS 3700 2018. So the characteristic strength or flexural tensile strength FMT dash for unreinforced and reinforced or pre-stressed masonry wall shall be as follows. So we have some different cases for how much is the capacity or flexural tensile strength of the masonry wall. Under action resulting from wind or earthquakes, loads, or similar force of a short-term transit nature, and where any simultaneous force due to vertical loads FD is not a negative value, which means there is no net tension force on the wall. So this means, just to interpret that, so if we have a wall and we have some horizontal or lateral loads from earthquakes or wind or any similar force for short term, okay, and we have a vertical force FD, but this force is compression, so not tension. The capacity will be according to the following. So the capacity or the flexural tensile capacity at the mortar joint for clay, concrete, calcium silicate masonry, the value will be less than or not greater than F 0.2 MPa. So F MT dash will be less than or equal to 0.2 MPa for clay, concrete, or calcium silicate. For autoclave aerated concrete masonry with thin bed joints, the value will be a little bit higher to be 0.26 MPa. So in this case, if MT dash is less than or equal to 0.26 MPa. For special masonry, the value should be from the test according to Appendix D, but it should be not greater than 1 MPa. So for special masonry, you need to follow test from Appendix D, the values from test according to Appendix D, but should be less than or equal 1 MPa. So the tensile or the flexural tensile strength of masonry walls in general is capped at 1 MPa. Okay, and this case only for special masonry. For other types of masonry, it will be less up to 0.2. Okay, then second, so the first one was for mortar joints, the second one for interfaces with other material. So if there is any interface with other material, Appendix D, again, the result from Appendix D should be followed. Okay, so the value here, FMT dash, is from tests according to Appendix D. In other cases, the design characteristic flexure tensile strength shall be taken as 0. So if the results or the test are not available, take if mt dash equal to 0. The life load shall not be considered to be short-term transit nature because the life load is applied for longer time than wind or earthquake. So the life load is not, this one is important here. Life load is not a not a short term transit load. In other cases, the design characteristic flexure tensile strength shall be taken as 0. So in any other case, from mortar joint with clay, concrete, calcium silicate, or at interfaces with other material, the value can be taken as 0. So this means that the value is small to be ignored, small enough to be ignored. Okay, so let's now design for one-way vertical bending. So the one-way vertical bending, the example or the picture we show earlier. So if we have horizontal support at the bottom and top edge. So this is the structure of the wall. So the bending will be in this direction. The bending will be in this direction. So the wall will or might be cracked at this point here. So this is our vertical bending. So to design for one-way vertical bending, we need to satisfy this formula from the standard. So MDV should be less than or equal to MCV, where MDV is the design vertical bending moment. So this is MDV is the applied moment on the wall from your analysis should be less than or equal to the capacity of the wall, which is the vertical bending moment capacity of the member. So similar to any design in steel or concrete or timber, the design or the applied moment less than or equal to the capacity. And V for vertical. So we have also two cases to satisfy this condition. If MT dash more than 0, so it can be 0.2 or 0.26 or 1. The maximum is 1. This was from previous slide. So MCV should be calculated using the two formulas. MCV equal to phi FMT dash times ZD plus FD times ZD. And the other value is 3 phi times FMT dash times ZD. Okay, so the value of MCV will be the lesser or the smaller of these two. So we need to calculate the two values and then select the smallest or the smaller from them. Okay, so phi FMT dash is the flexure tensile strength we calculated earlier. And the other parameter will be defined now. So these two are the flexure tensile strengths. So this only if MT dash has a value, because if MT dash doesn't have a value, so the formulas are not applicable. So the other condition or the other case, if we have the value of FMT dash equal to 0. So here MCV will have only one value, which is FD times ZD. So if the value of FMT dash equal to 0, so this will be our design or the capacity moment of the wall, where FD shall not be taken as greater than 0.36 MPa. So also because we have FD here, FD should be not more than 0.36 MPa. So this is the value of the FD. So let's see the definition of the parameter given in these formulas. So phi is, as you know, any phi is the capacity reduction factor. Here in this standard, phi can come from or can be obtained from clause 4.4. For FMT dash, it is the characteristic flexure tensile strength of the masonry, which can come from clause 3.3.3, which we discussed earlier. ZD is the section modulus of the bedded area. So for example, if this is our bricks, let's see it in 3D. So we have other bricks as well. So our bedded area will be this area. So this is our bedded area in this case. So you need to find, if you have, this is T, for example, and this is B. So you need to find Z of the bedded area equal to ZD. So ZD is the section modulus of the bedded area in millimeter to the power 3 per meter. FD is the minimum design compressive stress on the bed joint at the cross section under the consideration. So FD is design compressive stress. Okay. So ZD section modulus, FD design compressive strength. And the design compressive strength you learned earlier in the comparative design of unreinforced masonry wall can come from clause 7.4.3.3. We have also two cases for FD. If the top of the wall is not laterally supported, the design compressive strength at the top of the wall. So if the wall not laterally supported, FD will be at the top of the wall. If it is laterally supported at the top edge, so it will be at the distance equal to half of the height of the wall below its top lateral support. So almost in the middle. In normal cases, it is in the middle of the wall. So if the top of the wall not supported, take the compressive strength at the top of the wall. If the wall is supported at top edge, so the design compressive strength or stress will be at a distance of half of the height below its top lateral support or in the middle of the wall. FDZD is a pre-compression in the masonry due to its self-weight or superimposed load, and we need to apply a reduction factor of 0.9. FD not to be taken more than, again, 0.36 MPa. So FD is not taken to be less than 0.36 MPa. And the definition of FDZD is the pre-compression in masonry due to its self-weight. So when you apply, or put it here, if this is our wall, so we have applied, or there is applied load here due to self-weight of the wall. So there is some pre-stress or pre-compression. Pre-compression inside the wall due to this self-weight. So this pre-compression will help to resist the tensile stress. The tensile stress is applied. Okay. So this is the definition of the parameter and the two formulas or three formulas we have here. Again, the vertical bending moment capacity of the member. We have two cases. If we have a value of FMT dash, so we have two values to take the lesser of them. And if MT dash is equal to 0, so the value is FD times ZD. where FD is compressive or design compressive strength at the top of the wall or at the middle of the wall based on the boundary condition. So let's go through an example of the for the vertical bending. Do you have any question, guys? I think we have someone joined.
No, sir.
Thank you.
No.
I read this. Sorry, I can't read your full name. Arid, do you have any question, Arid? Anirud?
Yeah, no.
Okay. If you have any question, guys, just let me know, please.
Sure.
Okay, so let's go through the first example we have today about the vertical bending. So as you can see, in this example, we have a rectangular clay brick wall. The width of the wall is 110 millimeter. The height of the wall is 3000 millimeter. The width of the wall is 4000 millimeter. So if we put the dimension here, so this is our wall. So the width of this wall 110. The height of this wall 3000. The width is 4000. So this is the dimension given to us. The characteristic compressive strength of the brick FUC dash is 20 MPa. The wall is bonded with M2 mortar, 10 millimeter thick, full bedding, and no joint racking. So we have three information about the mortar: 10 millimeter thick, full bedding, and no joint racking. The wall is simply supported along horizontal edges only and subject to a uniform lateral wind pressure. Assuming that the self weight of the wall is 2.2 kilonewton per meter, we need to find per meter square. We need to find or calculate the following. Number one, we need to find the vertical bending moment capacity, MCV, of the wall and the maximum lateral pressure that the wall can withstand. Okay, so this means just adding one page here. Okay, so just to quickly interpret what we have here. So the idea is we have a wall. The width of this wall 110 millimeter again. The height 3000 millimeter. The width is 4000 millimeter. The self weight of the wall equal to 2.2 kilonewton per squared meter. And the wall, as you read, is supported along its top edge or only horizontal edge. So we have top edge and bottom edge. So this wall is susceptible to bending, vertical bending or horizontal bending, similar to what we was explaining. So because we have one support at the top here and one support at the bottom here, so we have only one way vertical bending. So the wall is susceptible to or subject to one way one way vertical bending, and the wall will crack or break at the mid height here somewhere. So this is what we expect. So what we need to find, or what is the requirement? Find the vertical bending moment capacity MCV. So we need to find how much MCV. This is our first one. Second one, using this information MCV or the capacity, we need to find how much is the maximum lateral wind pressure or earthquake pressure on the wall. So we need to find if we apply wind or earthquake load somewhere. So how much is this value? For example, W. So what is W max? So the second is maximum lateral loads on the wall. Okay, so let's start our calculation or our formulas. So the formula, if we go back here, so this is our formulas. So we have the vertical bending moment. So the capacity is MCV is the lesser of these two values. So we need to find the parameter here. So if we go through the calculation now, so we have phi equal to 0.6 from table 4.1, and we have FMT dash is 0.2 because we have clay masonry. The clay masonry was mentioned here, clay brick wall. So because it's clay, so we have FMT dash. So if we have a value of MT dash equal to 0.2 MBA, so we have our formulas to use are, as I show you, we have MCV will be the lesser of 1. Let's put it underneath here. So we have number 1, phi FMT dash ZD plus FD ZD. Number 2, we have 3 phi FMT dash and times ZD. So this is our two formulas. We will pick the lesser. So phi is 0.6, FMT dash 0.2 MBA. So the next is ZD. ZD is section modulus of the bedded area. The section modulus, because the bedded area is a rectangular. So the bedded area is the horizontal bedding because our moment in the vertical direction. So the resistance will come from the horizontal bedding. So the horizontal bedding, do you know the dimension of the horizontal bedding? The horizontal bedding is equal to the width of the wall, which is, or the thickness of the wall, sorry, which is 110 millimeter, times the whole width of the wall, which is 4,000 millimeter. So this is the resistance of the bedded area or the moment or the mortar area. So Z equal to BD square over 6, where B is the width of the total width of the wall, 4,000 millimeter, and D is the thickness of the wall, which is 110 millimeter. So ZD equal to 4,000 times 110 squared over 6 give us 8,000 8067 times 10 to the power 3 millimeter cubic. This for 1 meter of the wall, 1 meter width of the wall, or for each 1 meter of the height of the wall. Okay, so anyway, again, Z should be millimeter cubed over for each millimeter. So this means that you take 1 millimeter of the height. Okay, so you are not calculating for the whole height of the wall. We only calculate for 1 meter height of the wall. Okay, so this for ZD. So if we look at the formula, we know phi, we know FMT dash, we know ZD. So the last thing we need to find is how much is FD. So FD is the minimum design compressive strength. So let's look at this note here. Since the wall is simply supported along its horizontal edges, it is assumed to be subject to a uniform lateral wind load pressure. The maximum bending moment occurs at mid-height of the wall. Thus, FD is evaluated at the bed joint closest to mid-height of the wall. So this is conforming with the statement earlier here. FD is the minimum design compressive strength at the bed joint at the cross section under consideration according to these two cases. So if the wall is laterally supported at its top edge, because this is our case, the design compressive strength will be at the distance equal to half of the height of the wall below its top lateral support, which means almost in the middle of the wall or the mid height of the wall. That's why FD will be calculated as the mid height of the wall. So let's calculate FD. So the self weight at mid height will be 1.5 times 4 times 2.2. So the self weight was given 2.2 kilonewton per square meter, right? So in kilonewton, if this our wall, so the wall height was 3 meter and the width was 4 meter. So we need to find the self weight or the resultant of the self weight at here, at this, on this area. So how much is the height of the wall? Above 1.5 meter and below 1.5 meters. So we are looking at self weight here, and we need to find the resultant. So it will be the height of half of the wall or h of the wall over 2 times the width of the wall w times the self weight in kilonewton per square meter. This gives us a value of 13.2 kilonewton. AB or area of bedding will be 4,000 or 4 meter times the width or the depth of the wall, the thickness of the wall or the thickness of the bedding, which is 110 millimeter. So it will be 4,000 times 110, give us a value of 440,000 millimeter square. So the compressive strength at mid height will be 13.2 times 10 to the power 3 to make it Newton over the bedding area millimeter square. So the value of FD is 0.03 MPa. And the standard asked to apply for a reduction factor for FD of 0.9. So the value of FD equal to 0.9, the reduction factor times 0.03, which is equal to 0.27 MPa. Okay, so this is FD. After we got FD, if we return back to our formula, so now we know FD. So all the parameter for the two formulas are there. So we now can substitute in MCV to find the two values and select the smallest one. So we have 0.6 times FMT dash. So we have pi FMT dash 0.2. What is this value? This value is ZD or the section modulus time plus we have here FD, the compressive strength, times ZD. So this is the formula we have. This will give us a value of 1.18 kilonewton meter. So the capacity, the moment, the flexure or the moment capacity of the wall in the vertical direction equal to the first value is 1.18 kilonewton meter. This formula is 7.4.22. And the second or the second one we will select from. So this is our first one, and this is the second one. The second one is 3 times phi. So this is phi times FMT dash, the strength in flexion or in bending, times ZD equal to 2.9 kilonewton meter. So the second value we have is 2.9 kilonewton meter, and this formula is 7.4.23. So the value MCV, the final value will be the smallest, the lesser of 1.18 and 2.9, so it will be 1.18. So this is our first requirement. MCV, or the capacity of the wall in vertical direction, 1.18 kilonewton meter. Do you have any question, guys, for this one?
No, sir.
Thank you. Hello, Ruban. Hello, Sudip. Thank you for joining. Do you have any question, Sudip and Ruban and Aniro?
No, sir, we are okay. Yep.
Yeah, that's fine.
Okay, that's good. Okay, so this was our first requirement. What was our second requirement? Our second requirement was how much is the maximum load that can be applied to the wall. So how can we do that? We will do that reversely using MCV. So the idea is after we got MCV 1.18 kilonewton meter, so we need to find the maximum load capacity. So if we return back to our calculations, so if this our wall, so the wall is supported from top edge and bottom edge here. So we have one support here, one support here. So this is the structure analysis of this wall. Sorry, the structure representation of this wall, because we don't have any supports on the vertical side. So the idea is this is H, or the height of the wall, and this is W. So W will be something like that. So what is the moment in this case? If you have a slab or beam simply supported and has a load of W, so how much is the maximum moment? This will be the moment.
WH square by 8.
Yes, W L squared by 8. This is our moment. So the idea is we will use MCV as the maximum applied moment on the wall. How this happen? Because the design of the wall, if you can see here, our first formula, the design moment should be less than or equal to the capacity. So the maximum moment that the wall can withstand will be MCV. So here, MDV will be equal to MCV. So the value of MDV will be equal to 1.18. And how much is the maximum applied moment in formulas or structure formulas? WL squared by 8. So the idea is we will equalize MDV or MMX equal to MCV equal to WH squared over 8. So W max over 8. So this is our formula to use now. What we know in this formula? In this formula now we know that we have MCV 1.18 kilonewton meter. We have the height of the wall 3 meters. So now we can find W max. So to find W max for a vertical simply supported beam subjected to uniform lateral load, the maximum bending moment is WH squared over 8, where W in kilonewton per meter. So since the vertical bending moment capacity is known equal to Mmax, so we equalize it to MCV. So this is what we have done here in this formula. So now, if we substitute here, 1.18 equal to W max times 3 squared over 8. So W max will be equal to 8 times 118 over 3 squared, give us a value of 105 kilonewton per meter. So this is the value in kilonewton per meter, but for W here, we need W max. It is over meter or it should be over meter squared? It should be distributed over meter squared. So how to distribute it over meter squared? If we divide over the width of the wall, so we have W max in kBA equal to 1.05 kilonewton per meter over the width of the wall, 4 meter, give us a value of 0.2363 kBA or kilonewton per square meter. So the idea is here, if you don't pick it up, so the idea is this moment is for or per meter. So what is per meter? So like it's like we take one strip of the wall equal to 1 meter width. So if we want to extend that for the whole wall, so what we need to do, divide by 4 meter. 4 meter. So here the 4 meter is the width of the wall. So if we look here again, W max equal to MCV times 8 over H squared. So we find the value of the load in kilonewton per meter and divide it by the wall width, which is equal to 4 meter. We find it as 0.263 kVA. So is there any question, guys, for this example? So the second requirement is just application of the bending moment WL squared over 8 using the value we calculate in the first requirement MCV. All good up to here?
Yes, sir.
Okay, let's go to the second bending or the second bending behavior today. The second bending behavior is the horizontal bending. So the first was vertical bending of the wall. The second is horizontal bending of the wall. When the horizontal bending occur, if we have wall supported at its vertical edges. So we have vertical support here on the left, vertical support here on the right, and no horizontal support. So we don't have any horizontal support here. So what is the expected flexure, or what is the expected bending for this wall? The expected bending of this wall is horizontally. So the wall is supported here, and the wall is supported on the other side here. So it will bend in this direction. So when the wall bend in this direction, so there will be failure at the middle of the wall like that. Okay, so we have horizontal support here. So the wall will bend in this direction, and because the wall is not strong or not very good in bending, so we might have failure or cracks in the middle here. Okay, this is different from what we explained in the vertical. So just to compare with the vertical, what was the vertical bending or when the vertical bending occur. The vertical bending occur to compare because or when we have horizontal supports or horizontal edges are supported. So here we have the vertical end support, here we have the horizontal end support. So the wall will be, this is our wall, and the bending will happen in this direction. So the wall will crack in the middle here. So here in the wall, we have horizontal cracking. Here we have vertical cracking. Here in the first step or the first type was vertical bending. Here we have horizontal bending. Because the vertical bending will cause horizontal cracking and the horizontal bending will cause vertical cracking. Okay. So the main characteristic or the main feature of this one that we have vertical line of supports for the wall and no horizontal lines. So let's have also look at the notes here for one-way horizontal bending. So as you can see, this is the two vertical supports. Okay, and the crack, if the crack happen, the crack will happen like that because the wall will bend in this direction. So this should be in 3D, but anyway, I think you can understand that. So the wall will bend in 3D out of plane. Okay. So the horizontal bending may fail either through the mortar joints or partly through the joints and partly through the masonry joint. So if you look here to the previous one, the failure can happen in the mortar or in the brick unit itself. So it can happen to the horizontal joints or vertical joints or the bricks. So we have three types: mortar joints or partly through the horizontal and vertical, or this one is the mortar horizontal and this one is vertical joints, and partly through the masonry unit. So we can have three types of failures for this wall. All pre-bends must be completely filled. So as you know, the pre-bends means the vertical mortar joint like that. So all this one pre-bends should be completely filled. In this type of wall, you cannot have partially filled or not filled joints. So need to be all completely filled. So the wall also must comprise a minimum of 4 continuous cores of masonry acting together in horizontal bending. So we need to have 4 courses acting together for horizontal bending. So the condition or the formula to design the wall in horizontal bending is MDH less than or equal to MCH. Similar to the first type of bending, but we have H here. H is for horizontal. So same idea, the design horizontal bending moment should be less than the horizontal bending moment capacity. So again, M design less than or equal to M capacity of the wall. But because it is horizontal direction, so we give it the symbol or the subscript H. So let's go through how to find the values of MCH. The value of MCH, we have two cases. For masonry constructed of other than AAC unit, autoclave aerated concrete units, will be the list of 3. So in this case, we have MCH the least or the smallest of three values. The first value is the value here, MC H equal to 2 times phi times KB times root FMT dash times 1 plus FD over FMT dash times ZD. The second value is 4 times phi KB root FMT dash ZD, or the last value is 5.44 FUT dash ZU plus 0.56 FMT dash ZDB. So these are the values, three values we have. If you remember, what is FMT dash? FMT dash was 0.2 or 0.26 MBA. For this case, because it is for the first one, we have only clay or others for other from AAC, so it will be 0.2. FMT dash is the flexural tensile strength of the masonry. So we know this one. And we know FD. What is FD? FD was the compressive or design compressive strength. And ZD was the section modulus of the bedding area. So this three we have used earlier in the first example. So we have all of this. So the new thing here is KB. So the new thing we need to know is KB. And also we need to find what is ZB here and ZU and FUT dash. So FMT dash was known before, but we need to find this new parameters. For autoclave rated concrete or AAC masonry with thin bed mortar, we have only one formula. This is the formula we have. So also we need here to know what is FUT dash. Okay, so this is the formulas we need to use. And let's go through what is the parameter needed to finalize the calculation. So KB is the list of three values. KB equal to SCB over TU and KB equal to SCB over HU and KB equal to 1. So you will calculate the three values and select the list or the least of them. So what is SCB? SCB is the minimum overlap of masonry unit in successive courses. So as you know, mostly the overlap is half of the brick. So if this two successive courses, so this is the overlap. TU is the width of the masonry unit. So if this our in 3D unit, so this is the width of the unit. HU is the height of the masonry unit. So this is the height of the masonry unit. So we have height of the unit, width of the unit, overlap between the two courses. So these are the value. If we know SCB and TU and HU, you can find the value of KB and select the smallest of them. Okay, so this for KB. FUT dash is the characteristic lateral modulus of rupture of the masonry unit in megapascal. So it is in MBA, characteristic lateral modulus of rupture. Using clause 3.2, in the absence of test data, the design characteristic lateral modulus of rupture shall be taking or not exceeding 0.8. So FUT dash will be less than or equal to 0.8 MPa, which is lateral modulus of rupture. Lateral modulus of rupture, we have, if you have, this is your brick. So the brick have two direction of bending. If it bend in this direction, so the factor or the modulus of rupture is the normal one. This is modulus of rupture if it bend in this direction. The lateral modulus of rupture means if it is bending in the other direction. And I can better draw it in a different diagram. So if it bent in this direction, like horizontally, so this bent in horizontal direction, and this one bent in vertical direction. So if it bent in horizontal direction, the modulus of rupture is called lateral modulus of rupture. Okay, so we have the lateral modulus of rupture. Will come from clause 3.2. ZD is the section modulus of the bedded area in cubic millimeter per meter length. So ZD is millimeter cubic over meter. ZU is the lateral section modulus of the masonry unit in cubic millimeter per meter length. So again, in millimeter cubic by meter. For solid or core units, the gross section. For hollow units, the face shell dimension. So if it is solid, so the cross section. If it is hollow, so as you know, we have some bricks has hollow. So if it is hollow, only take the face shell. So the face shell mean only these two parts. ZB is the lateral section modulus, also in cubic meter per meter, based on the mortar contact area of the pre-bend joints. So we have three section modulus, ZD, ZU, and ZB, depending on the unit. The masonry unit, and depend on the bedded area, and depend on the contact area of the pre-bend joints. In the example, we will know how to calculate each of them. So if we go back here again, now after we know KB and we know FUT dash and ZU, ZB, we can find the value of MCH, which is our capacity. And here for aerated concrete, we can know FUT, so we can know MCH. So these are the main things to find. So let's go to the example. It is similar example, rectangular clay brick wall, 110 millimeter thick, 3000 millimeter high, 4000 millimeter width. So this is our wall, 3000, 4000, and the thickness is 110 millimeter. But here, the not this one, the characteristic compressive strength of the bricks FUC dash is 20 MPa. The wall is bonded with M2 mortar with 10 millimeter thick, full bedding and no joint racking. Use brick 220 times 110 times 76 millimeter. This all similar to what was given in the first example. The new thing is This wall is simply supported along its vertical edges only. So the vertical edges, this edge and this edge. No support here and no support here. So that's why this problem is under horizontal bending. So the wall is simply supported only along its vertical edge, subjected to uniform lateral wind pressure. Calculate the horizontal bending moment capacity of the wall MCH. So the only requirement here is how much MCH. So MCH will be equal to the lesser of three values we just mentioned or we just described earlier here. So we have three values of MCH. Calculate each of them, select the smallest. So how to calculate these three values? So the first thing is how much is phi? Phi is 0.6. FMT dash 0.2 MBA. This includes 3.3. FUT dash is 0.8 from close to 3.2. So we can have a look quickly on the standard. Can you see the standard now? So if we look at section 3 give us some of the design probabilities. So guys, can you still see my screen?
Yes, sir.
Okay, that's good. Thank you. Imanto. So these are the design characteristics like compressive strength and so on. So let's look at clause 3.2. In absence of test data, the design characteristic can be taken as 0.8. So this for FUT dash, the lateral modulus. Okay, so this is FUT dash, and phi is 0.6 in table 4.1. So if we go to table 4.1, for unreinforced masonry, we are under flexure or under shear or under what? We are under flexure. So how much is phi? 0.6. So 5.6 FMT dash 0.2 FUT dash 0.8. Then how much is ZD? ZD is B. So if our wall under horizontal bending, this is the bedded area that will how much B? B is the height of the wall. How much is the height of the wall? 4 or 3,000 millimeter. How much is the width of or thickness of the wall? 110 millimeter. Just add a page to explain. So if this our wall, so this is 3,000, 4,000, and thickness is 110 millimeter. This wall is only supported from this side and from this side. So the structure or the bending of this wall will be here, here. So it will bend in the horizontal direction like that. So the crack will happen like direction will of the which direction of the bedded area that will resist. The bedded area that will resist is this cross section here. So this is the cross section that will resist our moment. So if we have horizontal moment, the vertical bedded area will resist. So how much is the width of the vertical bedded area? 110. How much the height or the width of the bedded area? Not 4,000 here. It will be how much? 3,000 millimeters. Okay, so if we return back to the calculation, so how much B for the bedded area? 3,000. How much D for the bedded area or T? 110. B or T 110 millimeter. So ZD equal to BD square over 6. So ZD will be 3,000 times 110 squared over 6, give us 60, 50 times 10 to the power 3 millimeter to the power 3 over meter. So each meter height, or sorry, each meter width of the wall will have ZD equal to 60, 50 times 10 to the power 3. Okay, ZU will be equal to ZD equal to 360, 50 because we have full bedding and no racking. So no racking. So if we have full bedding with no racking, so ZU and ZB will be equal to ZD equal to 60, 50 times 10 to the power 3 millimeter over meter, millimeter cubic over meter. So ZB also for of the pre-bend joints 60, 50 times 10 to the power 3, same as ZD, since we have full bedding and no racking. Okay, so we will take Z for the units and for the bedded area same, because we have full bedding and no racking. So do you understand what does this mean? What does this mean that we take ZB and ZD, sorry, ZB and ZU equal to ZD? Do you have any reason for that?
No, sir.
Okay, this means that we have three elements, right? The unit and the pre-bend joint and the horizontal joint, right? So this condition means that the critical of the three elements will be the value of ZB. So because this is the resistance, so this line is the resistance, the pre-bend in this direction. So this will be the critical one of them. So we will assume all of them same, because if you have three things, one of them will fail first. So which one is the critical? This one is the critical. So because we have full bedding and no cracking, so the critical of the three will be ZD. So we take all of them as ZD. Okay. So this condition, when we have full bedding and no racking, we have ZU equal to ZB equal to ZD. ZU of the masonry unit itself. ZB is for the pre-bend or bare bend, the bare bend joint, and ZD is for the bedded area. Okay. So
Can you explain what is racking?
no, racking means in some joints they leave this with no filling. So this is what is mean by racking.
Okay, sir. Thank you.
Thank you. So after we got ZB, what is the next to find? The next to find is FD. So the minimum design compressive stress. Since the wall is not laterally restrained at its top, ignore the self-weight FD at the top of the wall. So if you remember, if we can go back to it, for the first example or for the explanation here, FD is the minimum design compressive strength. We have two cases. If the top of the wall is not laterally supported, the design takes the design compressive strength at the top of the wall. So in this case, in this problem we are solving now, so our wall is not supported at the top or the bottom. It is only supported at the vertical edges, right? So FD will be at the top here. So at the top here, we will, because at the top, in this case, at the top edge, there is no self-weight. So if there is no self-weight, how much FD? FD can be taken as 0. Okay, so FD in this case can be taken as 0 because the wall is not supported at top. The bare bend is bend spacing factor KB. We have 3 values if you remember from the calculation. So the 3 values depend on 3 parameters: SB and TU and HU. SB is 110. It is assumed that the masonry unit overlap by half of their length. So if you remember from the explanation, SB is the overlap between the two successive courses. So SB will be half of the brick length. So how much is the brick length? It was given as 220 or 20, 220. So that's why SCB is 110. What is TU? TU is the width of the brick, which was 110. How much HU? HU is the height of the brick. What is the height of the brick given to us? 76 millimeter. So these are the 3 values. So KB will be the lesser of SCB over TU, which is 1. SCB over HU, 110 over 76. So it will be also 1. So what is the maximum? Sorry, what is the lesser of them? The lesser, which is 1. Okay, so because if you go back, KB cannot exceed 1 because the list of this 3, even if this 1.1, 1.2, so this 1. So the limit is 1. That's why KB in this example will be taken as 1. So now, what is the maximum horizontal capacity of this wall? MCH will be the lesser of the 3 values given in formulas, given in equation 7.4.3.2. So if we go to this page or this close to C, so this section number 7. So this is the design of member and bending. This for vertical bending, we already finished. This for horizontal bending. So we have MCH. This is the first formula, second formula, and third formula. Okay. So 7.4.32, 3, and 4. This for the clay. So because we have clay brick, so we have one of the three values, number 1, number 2, number 3. 7.4, 0.3.2, 0.3.24. So the values are 2, pi. So just to remove this one here. So the first value of MCH, 2 times phi times KB times root FMT dash times 1 plus FD over FMT dash times ZD. So this is ZD, 60, 50 times 10 to the power 10. FD 0, FMT dash 0.2, FMT dash 0.2, KB1, phi 0.6. This value is 3.25. Second value is equal to 4 times phi times KB times root FMT dash times ZD. So this is ZD, FMT dash KB and 0.6 give us a value of 6.49. The third value is phi times 0.44 times this is FUT dash times ZU. So this is ZU, this is FUT dash plus this is 0.56 in the formula times FMT dash times ZB. So ZB equal to ZU equal to ZB. This is FMT dash, so the value is 1.68 kilonewton meter. So what is the lesser value? MCH equal to the lesser of, the least of 3.25, 6.49, and 1.68 kilonewton meter. So the value is this value. So MCH 1.62 millimeter. Sorry, kilonewton meter. This is the maximum value. You understand this one, guys?
Yes, sir.
No problem. Okay, that's good. So this our first two bending types. So the third one is two-way bending. So for the first two types of behavior, we have one way vertical and one way horizontal. So the third one will be two-way bending. So for the two-way bending, the actual cracking pattern depend on the support condition on each side of the wall panel. So in this case, we will have if there is vertical compression, if D is not 0, so let's see the definition again. So FVD is the minimum design compressive stress on the bed joint at the cross section under consideration. So if we go to clause 7.4, the value of the design on the bed joint for use shall be the compressive strength under consideration resulting from the minimum design compressive forces that act simultaneously with the loads and force producing in bending compression on the member. Yes, so the minimum applying. So if you design the wall for compression as well, so you need to take this in consideration. Okay, Ruben?
Okay.
Yeah, but there is another the main condition is here. If you can read here, if the top of the wall is not laterally supported, so the design compressive stress at the top of the wall. So it will be designed for the compression coming from above. But here, if the wall is laterally supported from top, so you will take the design compressive strength at the middle or at the mid height of the wall. Okay, but for these two examples we study today, we don't have any other vertical loads. That's why we only depend on the self weight. So if self weight is if self weight only, so the top will not have any self weight. But if there is design compression force, you need to take it into account. Okay. Thank you, Ruban, for your question. Okay, so if we return back to our third type of behavior, the third type of behavior is the two-way bending. So the actual crack pattern depend on the support condition on each side of the panel. So the two-way bending of the wall similar to two-way bending of slabs. If you have studied concrete slabs, so same idea. So depend on what the condition of the four sides. So here, for example, we don't have no top support and no vertical support on the left, but we have this horizontal, this vertical, and this horizontal. So the crack pattern depends on the supports. So this is an example design of two-way bending. If we have line of support from the roof at the top and line of support from the base and line of support from the left side. So the crack pattern will be, as you know, something like that. So this fold and this fold, this will two meet at one point. So for example, if this 450, 450, 450, 450, and then this will go straight like that because there is no support here. Okay, so this will be the crack pattern of the wall in two-way bending, similar to slabs or solid slabs. So here's some notes about the two-way bending design. The wall is designed as a rectangular panel with lateral supports at least along its base and one of its vertical edge. So to have two-way bending, you need rectangular panel with lateral support at least along its base and one of its vertical edges. So the base and one of the okay. So if you have something like that, so you will have two-way bending. The wall is of single leaf or solid construction or cavity wall construction, with each leaf of the cavity wall being of single leaf or solid construction. So single leaf means if we have one this is the wall width, or so this is two single leaf. Cavity wall, if you have two together connected at somewhere and you have two leaves, so you have a space between them. And solid construction if you have more than one leaf. Okay, so this is the wall. The requirement for robustness are satisfied for this wall. The construction and detailing of the wall are such that of the requirements of clause 7.4.2 and 7.4.3. If the wall has an opening, the panel on each side of the opening is checked independently. So if we have a wall and we have an opening, so you need to check this part alone and this part alone. Okay, so this what is meant by this notes. The lateral load capacity of the masonry other than rated concrete, WD should be less than W, where W is the following: 2AF over LD squared times K1 MCH plus K2 MCD. So the design load should be less than or equal to W. This is the condition, where W, or the capacity, lateral load capacity, is using the formula from 7442, where 2W equal to 2AF over LD squared times K1 MCH times plus K2 times MCD. So what we know here from previous calculation, what is MCH? Is the horizontal bending capacity of the wall. MCD will be the diagonal bending capacity of the wall. So other parameter K1, K2, AF, and this actually alpha F. Alpha F and LED will come later. Lateral load capacity of AAC masonry will be using this clause, W equal to 12H over L BV MCV over H squared plus BH MCH over L squared, where MCV and MCH, this is the vertical bending capacity, and this one horizontal bending capacity. Okay, so let's look at the parameter. The parameter here is the coefficient for out of plane lateral load resistance, W. So if we don't have opening, we have 4 cases for no opening, 2 cases for with opening. Number of vertical edge supports, both or one or both. Slope factor alpha. This slope factor is for the crack pattern slope. Aspect factor alpha F, K1 and K2. So depending on if you have vertical support or not, if you have or what is the angle or the slope of the cracks, and the aspect factor alpha F, which is related to alpha or based on alpha, you can find K1 and K2 from this table. Okay, so this some definition or explanation of alpha and the factors in the table. The values of the aspect factor alpha F are given in table 7.5. The aspect factor is a function of the slope factor alpha, which in turn is a function of the assumed slope of the crack line. So if this was our wall, so alpha is the slope or function of the slope assumed. G is the slope, the design length LD, and the design height HD. So LD is the design height, LD is the design length, HD is the design height of the wall. The horizontal bending moment capacity, MCH, determined in accordance with the previous calculation we did, close 7.4.3.2, modified by a coefficient K1 representing the degree of rotational restraint for the first supported edge of the wall. Because MCH and MCH and MCV was for horizontal only and vertical only bending, but here because we have a combination of horizontal and vertical support, so we need a coefficient of K1 to represent the degree of rotational restraint for the first supported edge of the wall. The diagonal bending moment capacity, MCD, per unit length of the diagonal crack line, determined in accordance with 7.4.4.3, modified also by a coefficient factor K2 representing the degree of rotational restraint for the second supported edge of the wall. Okay, so we have MCH and MCD. MCH for horizontal direction, MCD is for diagonal direction. So let's look how to find MCD and MCH. MCH was calculated earlier, so let's look at MCD. So for the diagonal bending moment capacity MCD given by formula 7.4.4.1, we have MCD equal to phi ft dash ZT, where ft dash is the equivalent characteristic torsional strength, which is equal to 2.25 root fmt dash plus 0.15 fd, where fmt dash and fd discussed earlier, fmt dash is the flexure tensile strength and fd is the minimum design compressive strength. So Ft is the equivalent characteristic torsion strength. So Ft dash is the torsional strength. So the torsional strength will be depending on Fmt and Fd. Zdt is the equivalent torsional sectional modulus using equation 7.4.432 and 3 and 4, where B is the height factor equal to HU plus TJ over root 1 plus Z square, and G is the assumed slope of the crack line, 2 times HU plus TJ over LU plus TJ. So if we go to the standard to see 7.4.3, the design of two-way bending. So this is formulas. So can you see the screen? Can you see clearly? Or maybe I try to. Okay, so this is the lateral strength, lateral load capacity of masonry wall, and this is the parameters. All the parameter can be found here: RF1, RF2, alpha, L naught, HD, and G. So for G, here we are at this one here. So G, sorry, I can't. I think. Yep. G is the assumed slope of the crack line, equal to two times HU plus TJ over LU plus TJ. HU is the height of the masonry unit, TJ is the mortar joint thickness, and LU is the length of the masonry unit. Okay. So I think it will not be question on this one, not just for to know how is the two-way bending design, but I think the focus in the example will be on the horizontal and vertical bending, okay? Because I think it is too complicated to find the two-way bending in an exam. All good?
Yes, sir.
Okay, so all the parameter can be found in the section 7.4.4.3, and let's go more other parameter. So LED is the design length of the wall. So we have also two cases or three cases for it. If the wall has only one vertical edge supported, so LED is the actual length of the wall. So if the wall supported only from one edge, so this will be LED. If both edges are supported, LED will be half of the actual size of the wall. So if we have two, this will be LED. So LED in this case, half of the wall. Okay. If the edge of the opening, LED, the distance from the edge of the wall to the edge of the opening. So if we have an opening, so this will be our LED. So LED will be only the length, actual length of the wall if we have only one vertical edge supported. The design height of the wall, HD, we have two cases. Top edge of the wall is not laterally supported, so the actual HD is the actual height of the wall. So if we have the wall, top edge not supported, so this is HD. The other case, if we have top edge also supported from a roof or something, so LED will be half of the wall. So if the top edge is supported, HD half actual height of the wall. So we can have LED and HD half if top and two edges, top and bottom, and two vertical edges are supported or laterally supported. Okay, so now let's look on the in-plane flexion and shear strength of the wall. So the wall in general case can can have in-plane and shear strength plus the vertical forces, so plus compression. So this means the horizontal force acting in plane of the wall. Okay, so if we have shear force or horizontal force in plane and vertical force in plane, we can have overturning or bending moment at this too. Okay. So what is the checks or what is the design required in this case? Before, what is the design in this case? These are the type or the expected straining action on the wall and the name of the wall. So this case is a shear wall case similar to the ones you design in the first project. So if the lateral wind or earthquake loads acting in plane of the wall, so this wall will have shear in this direction, which is parallel to the wall, and this wall can be called as shear wall. Other option, not shear wall, but it is retaining wall. For example, if you have a retaining wall like that, so you have earth pressure or water pressure from this direction. So the shear in this direction will be in the shorter direction, and this one is retaining wall. The third option or the third type is the wall with returns or diaphragm walls. As you can see, we add two returns or counterforts to the wall to make it more stable. So if you have a lateral wind here, due to these two supports here, so you will have vertical shear on the wall. This wall is called wall with return. So the one we are studying now is this one. Here, shear wall, which you have in plane and load from above or compression. So the standard give us some load combination to check the stability of the wall plus the strength. So we have some load combination for strength and some load combination for stability. For stability of the shear walls, the basic combination for ultimate limit state used in checking stability shall be as follows for long term, and combination factor are given in table 4.1. So the first case for combination that produce net stabilizing effects, so ED for stability is 0.9 G. So for stabilizing effects, we use the value of 0.9 G. For combinations that produce net destabilizing effects, so we have 0.35 G, 0.2 plus 0.15 Q, 0.1 G plus 0.15 Q, 1.2 G plus WU plus Psi CQ, and G plus EU plus Psi EQ. So this for earthquakes, this for wind, and this for life load, this for dead load. So the first one is for stabilizing, and the last four are for destabilizing. For strength, similar to any design of steel or concrete or timber, the basic combination for ultimate limit state and checking strengths shall be as follows for long term, and combination factor are in table 4, and all these combinations are in 1170.0, and also the stabilizing or the stability combination are 1170.0. So we have 1.35 G, 1.2 G, 1.5 Q, and so on. And for the reversal wind, 0.9 G plus WU, and for earthquake, G plus EU plus Psi EQ. So we have 5 or 6 of them. This for G, this for life load, Q, this for Q as well, this for wind, this for wind uplift, this for earthquakes. So these are the load combination for strengths, and this is the short-term and long-term factors, psi. So we have psi s for long-term, psi l for long-term, sorry, psi s for short-term, psi l for long-term, psi c for combination, psi e for earthquake combination. So based on what you are designing, floor or roof, and so on, you can find how much is the factor. So this is what I was talking about. What is the Schick's needs for in-plane shear of shear wall? So if you have in-plane shear, so you might have 4 failure modes. You need to look or you need to check. The first one is crushing at the toe. Second one is overturning at the toe. Third one is tension at the heel. And the fourth is shear capacity. So when you are designing a shear wall or masonry shear wall, you need to check this for at the crushing at two condition. You will study the vertical forces and horizontal forces. The vertical forces B 1.2 D plus psi C life load. The horizontal load F will be the wind load. So the check is B, the vertical load over AB, the bedding area, plus F is horizontal load times H, the height of the horizontal load, over ZD, the section modulus of the bedding area, should be less than or equal to phi Fm dash. We will see it later. For overturning, you have also two cases of loading, vertical forces. Here is overturning is one of the stabilizing effects or stabilizing condition of the load combination. So here for combinations that produce stabilizing. So because when the wall is overturning, you need to stabilize or make it stable. So the overturning at 2 is stabilizing effect. So the vertical load will be only 0.9 of the dead load. For the horizontal force, again, it is the wind load. So in this case, B, the vertical loads times B over 2 should be less than factor of safety times FH. So the moment of the vertical load should be equal to or more than the moment of the horizontal load. The third condition, tension at the heel. Tension at the heel, we have also vertical and horizontal load. For vertical forces, again, it is stabilizing effect. So B is 0.9 G dead load. Horizontal force is F equal to the wind load. So B over AB minus FH over ZD should be more than or equal to phi negative F dash MS. So this one and this one are almost similar, just here positive and negative. The shear capacity, also stabilizing effect. So we have vertical and horizontal. For vertical load, we have B equal to 0.9 D or dead load, and horizontal force F equal to the wind load. So F or V, the shear, should be less than or equal to VO or V naught plus V1. Okay, so these are the 4 cases we need to check for the in-plane wall. And these are the cases. So I think we can go through this in the next lecture. Okay, are you okay with that? We can continue from that in the beginning of the next lecture. Do you have
Yes,
any
sir.
question? Do you have any question, guys?
No, sir.
Or good? If you need anything, I can clarify in the next lecture. So if you have any query or any issues, just let me know. Ruban and Aniro and Sudib are good with you as well?
Yeah.
Yes.
All
Yes.
good.
Okay, thank you guys. Okay, guys, thank you for attending today, and I may see you in the tutorial later, and we'll see you next week. Thank you, guys.
Thank you, sir.
Thank you.
Thank you.
Thank you.